A primary or master name server resolves queries for the domain. It reads zone files to resolve queries. A secondary or slave name server resolves queries when the primary or master name server fails. To explain how to configure primary and secondary name servers, I will use a pre-built lab. In this lab, I have three systems, our HEL Server 1, our HEL Server 2, and our HEL client. Currently, our HEL Server 2 is configured as a caching-only DNS server. Our HEL Server 1 is configured as a forwarding-only DNS server, and our HEL client is configured as a DNS client system. The bind and bind utils packages are installed on our HEL Server 1 and our HEL Server 2. Currently, systems are configured to use these IP addresses. To learn how to set up this lab, you can check this video. The link to this video is given in the description. On our HEL Server 1, log in from the root account and verify the bind and bind utils packages are installed. For this, you can use the dnf command. When using the list option, this command searches the specified packages on the local system and prints the result. As we can see here, both packages are installed. Now let's verify the IP configuration. For this, we can use the IP command. To view the configured DNS server's IP address, we can view the /etc/resolveconf file. As we can see here, this system is configured to send DNS queries to the DNS server configured on the local system. Now, open the /etc/namedconf file and configure this system as a primary name server for the example.com domain. Currently, this system is configured as a forwarding-only DNS server. These two options configure this system as a forwarding-only DNS server. First, we need to remove these options. These options are not part of the default configuration. I added these options to configure this system as a forwarding-only DNS server. If you are editing this file for the first time, you will not see these options. We need to configure these two options. Configure this system's IP address here. This option configures this system to listen for DNS queries on the IP address 192.168.29.100. Add the local network's network ID here. This option configures the network whose hosts can send DNS queries to this server. Collectively, these options configure this system to listen and answer DNS queries from the network 192.168.29.0/24 on the IP address 192.168.29.100. To resolve queries, it uses the zone section. To configure this system as a primary or master DNS server for the domain example.com, we need to add a zone configuration in the zone section. A zone configuration starts with the zone keyword. After this, we need to specify the domain name. All zone configuration goes inside curly brackets and ends with a semicolon. Inside the curly brackets, we need to configure three options: type, file, and allow transfer. The type option defines the role of this server for this zone. To configure this server as the primary or master name server for this zone, we use the value master here. To configure this server as the secondary or slave name server for this zone, we use the value slave here. The file option defines the name of the zone file. The name server uses this file to answer DNS queries that belong to this domain. By default, the name server looks for this file in the /var/name directory. On the primary or master name server, we need to manually create this file in this directory. The allow transfer option defines the secondary or slave name server's IP addresses. The name server automatically transfers zone files to name servers defined in this option. If we don't want this name server to transfer zone files to any other name server, we need to specify the value none here. We will configure this option later when we will configure a slave name server. Save the file. Since we configured this system as the primary authoritative name server for the domain example.com, we need to create a zone file for this domain in the /var/name directory. This directory contains a zone file for localhost. We can use this file as a template to create the zone file. Since it is an important configuration file, we will not use this template. We will create this file from scratch after understanding its configuration. DNS saves its database in zone files. A zone file stores records of a particular domain in simple text format. A zone file stores resource records in lines. For each record, it uses a separate line. If you want to create a resource record in multiple lines, you must use parentheses. DNS process everything you put between an opening parenthesis and a closing parenthesis as a part of the line. Administrators use this feature to make the start of authority record more human readable. This is a start of authority record. We will talk about this record later in this video. When processing, DNS removes these parentheses and arranges these fields in the same line. DNS looks at this record like this. To separate two fields in a record, you can use either spaces or tabs. Generally, tabs are used for it. Tabs provide a more attractive layout and clearly indicate the added and missed fields. This file uses spaces to separate fields. This file uses tabs to separate fields. As we can see here, if we use tabs to separate the fields in the records, the fields look neat and descriptive. We can easily identify which fields have values and which fields are empty. A zone file contains three types of entries: comments, directives, and resource records. A comment starts with a semicolon and continues to the end of the line. You can add a comment to any directive or record. DNS ignores everything you write after a semicolon till the next line. If you put a semicolon at the beginning of a line, DNS ignores the entire line. If you put a semicolon in the middle of the line, DNS ignores everything that comes after the semicolon. This is how DNS looks at this file. A directive starts with a $sign. It works as a variable. It stores value. DNS replaces a directive with its value when it processes the zone file. There are two important directives: TTL and origin. This directive is mandatory. It defines a default time to live value for resource records. All resource records have this field. If you want to define a specific time to live value for a record, you can configure its TTL field. If you want to use the default time to live value for a record, you need to leave the record's TTL field empty. When processing records, DNS uses the default time to live value in all blank TTL fields. DNS service includes this value with each record it serves from this file. Other DNS servers and resolver systems that receive a record served from this file use this value to cache the record. For example, if the time to live value of a record is 1 day, resolver systems and other DNS servers can cache the record for 1 day. After that, they must have to retrieve the same record again. By default, this directive accepts value in seconds. If you want to specify the time in other formats, you need to use related keywords. These keywords are M for minutes, H for hours, D for days, and W for weeks. The following examples set this directive's value to 2 days in different formats. You can use whatever format you like. In the DNS database, a resource's name can be either a fully qualified domain name or a relative name. A fully qualified domain name is a complete name. It includes the names of all top-level domains till the root domain. It ends with a dot. You can access a resource from anywhere in the domain system using its fully qualified domain name. This is an example of a fully qualified domain name. A relative name is a host name. It may or may not include the parent domain's name. It does not end with a dot. In the DNS system, you cannot access a resource from outside the domain using its relative name. However, you can access a resource inside the domain using its relative name. These are examples of relative names. You can use both types of names in the zone file, but DNS will process only fully qualified domain names. If you use a relative name in the zone file, DNS automatically converts it into the fully qualified domain name before processing it. To convert a relative name into the fully qualified domain name, it uses the origin directive's value. The origin directive stores the fully qualified domain name of the domain. It attaches the domain's fully qualified domain name to the relative name as a suffix to make it the fully qualified domain name. In a zone file, you can specify a name in 4 ways. You can specify a fully qualified domain name, a relative name, a singlet symbol, and a blank space. If you use a fully qualified domain name, DNS uses the name as it is. A fully qualified domain name always ends with a dot. DNS uses this rule to identify fully qualified domain names in the zone file. If a name ends with a dot, it assumes the name is a fully qualified domain name and processes the name as it is. In this zone file, these names end with a dot. DNS will process these names as fully qualified domain names. If a name does not end with a dot, it assumes the name is a relative name and converts it into the fully qualified domain name. To convert a relative name into the fully qualified domain name, it uses the origin directive's value. It attaches the origin directive's value as a suffix to the relative name. In this zone file, these names do not end with a dot. DNS will process these names as relative names. It will use the origin directives value to convert these names into fully qualified domain names. If you use a single @ symbol in the name field, DNS replaces this symbol with the origin directives value. For example, this resource record has an @ symbol in the name field. When processing this file, DNS will replace this symbol with the origin directives value. If you use a blank space or leave the name field empty, DNS uses the previous record's name field's value. If we talk about this file, DNS will use the value example.com in the name field of these records. Let's understand how DNS will process the name fields of these records. This record has the @ symbol in the name field. DNS replaces the @ symbol with the value configured in the origin directive. This record's name field is empty. Because of this, DNS will use the previous record's name field's value here. By following the same rule, this record will inherit the name field's value from this record. The same thing will happen here and here. A resource record defines the characteristics and properties of an entity within the domain. There are many types of resource records. The main resource record types are start of authority, name server, mail exchanger, A, quad A, and PTR. Let's understand the meaning of each record in detail. The start of authority record defines the authoritative name server for the domain and configures its properties and characteristics. Since each domain needs a unique zone file, we cannot add more than one start of authority record in a zone file. We can add only one start of authority record in a zone file. It uses the following syntax. Let us understand this syntax field by field. This field specifies the domain or zone name. The name server whose name we specify in the name server field becomes the authoritative name server for the domain or zone whose name we specify in this field. Since we used an @ symbol here, it will be replaced by the origin directives value. This field defines the time for which other name servers or resolver systems can cache this record. If we leave this field empty, DNS uses the default value defined in the time to live directive. This field defines the class type of this record. There are three classes: in, ch, and hs. Currently, only the in class is used. The ch and hs classes were used when the Internet was an in-house project in the MIT lab. Ch stands for chaos. It is an MIT LAN protocol. HS stands for Hesiod. It is an information service used at MIT. In stands for the Internet that we use today. Currently, only the in class is used. CH and HS classes are used in special cases for specific reasons. This field defines the type of record. This field defines the authorized name server for this domain. It only defines the authorized name server for the domain. It does not map an IP address with it. To map an IP address with the authorized name server, we also need to create a host record for it. This field defines the administrative email address of the domain. You can use any valid email address in this field. Generally, administrators use the email address hostmaster here. It describes the purpose of this field. In other configuration files, the @ symbol is used as the separator in the email address. In a zone file, the @ symbol has a special meaning. DNS replaces the @ symbol with the origin directives value. If we specify the email address hostmaster@example.com, DNS will read it as hostmaster.example.com. To avoid this confusion, DNS uses the dot separator here. In this record, I use the email address hostmaster.example.com as the administrative email address. DNS will read this address as hostmaster@example.com. These fields control the zone transfer process. Before we understand these fields, let's understand what a zone transfer is and how it works. A zone transfer is a process in which a master nameserver transfers zone files to the slave nameserver. As we know, in the DNS system, we can create zone files only on the master nameserver. The master nameserver automatically transfers zone files to the slave nameservers when it receives zone transfer requests. The slave nameserver periodically sends zone transfer requests to the master nameserver. The slave nameserver uses these fields to define and control the frequency of the zone transfer requests. There are two types of zone requests: the complete zone transfer request and the start of authority record transfer request. The slave nameserver uses both types to speed up and optimize the zone transfer process. The first time, it makes the complete zone transfer request. The master nameserver transfers the zone file. The slave nameserver saves the received zone file. The next time, instead of making the complete zone transfer request, the slave nameserver makes the start of authority record transfer request. The master nameserver transfers the start of authority record. The slave nameserver compares the received start of authority record serial number with the locally saved zone file start of authority record serial number. If both numbers are the same, it assumes that the master nameserver's zone file is not changed. It keeps using the locally saved zone file. If both numbers are different, it thinks that the master nameserver's zone file has been changed. It sends a complete zone transfer request to the master nameserver. The master nameserver transfers the updated zone file. The slave replaces the locally saved zone file with the received zone file. This way, after the first time, a slave nameserver makes a complete zone transfer request only when the master nameserver's zone file changes. It uses the start of authority record serial number to detect changes in the master nameserver's zone file. Since the slave nameserver uses this number to detect changes, you need to update this number every time you make a change to this file. There is no predefined rule for this number. You can use any number from this range. Usually, administrators use the current date in the YYMMDD format and an incremental sequence number from the range 0 to 99 to generate a unique and updated serial number for every change they make in the file. For example, if we expend this serial number using this technique, we get these values. These values show this file was last updated on June 25, 2023. A 00 in the sequence field shows that this file was updated only once on June 25, 2023. If administrators update a zone file more than once per day, they can use incremental sequence numbers for every update. For example, this serial number shows the file was updated 3 times on June 25, 2023. The refresh time field sets the refresh time. The slave nameserver uses this time to determine how quickly it should check the master nameserver for an update. In this zone file, this time is set to 12 hours. Because of this, the slave nameserver checks for an update every 12 hours. If it gets an update, it asks for the next update after 12 hours. For example, the slave nameserver tries to reach the master nameserver at 12 a.m. If it connects, it will try again at 12 p.m. But if it fails, it will try again after the retry time. The retry time field defines the retry interval. If the slave nameserver fails to connect with the master nameserver, it can try again after this time. For example, in this zone file, this time is configured to 15 minutes. Because of this, the slave nameserver will try again every 15 minutes if it fails to connect to the master nameserver in a refresh cycle. It will keep trying until the expiry time. In this example, the expiry time is 3 weeks. Therefore, it will try to connect the master nameserver every 15 minutes until 3 weeks. For example, if it first tries on 12 a.m. of July 1, 2023, then it will try till 12 a.m. on July 22, 2023. If it succeeds on any try, it resets the refresh and retry times. If it fails to contact the master server till the expiry is reached, it stops working as a slave name server for the zone. After this time, it will not resolve queries for the domain. A slave name server resolves queries for the zone when the master name server is down. It resolves queries for the domain until the master is up or the expiry is reached. After the expiry, it does not resolve queries for the domain. At this point, since both the master name server and the slave name server are not resolving queries, the zone is considered dead. Resolver systems use the negative cache value to store negative responses. This value applies to all records served from this zone file. DNS provides this value in each answer. Let's take an example. Suppose, a resolver system asks this nameserver to resolve the name xyz.example.com. The server checks its zone file and finds no entry for the name xyz.example.com. It returns an error indicating the requested name does not exist and can't be resolved. It also includes the negative cache TTL field's value in the error message. The resolver system saves the answer in the cache and does not send a query to resolve the same name again until the negative cache time expires. In this example, the resolver system will not send a query to resolve the name xyz.example.com in the next 2 hours, starting from the time it received the response. For example, if it receives a negative response at 2 p.m., it will not retry until 4 p.m. for the same name. There are 2 types of name server records, authoritative and referral. An authoritative name server record authorizes a name server to resolve queries. A referral name server record diverts queries to the authoritative name server. Each authoritative name server needs both types of name server records. It requires an authoritative name server record in the domain zone file for which it resolves queries and a referral name server record in the parent domain zone file that forwards queries to this domain. Resolver systems can access an authoritative name server through referral name servers. DNS system organizes authoritative name servers in a hierarchy. Each authoritative name server resolves queries for its domain and provides a referral for the child domain. When an authoritative name server receives a query, it checks whether the query belongs to it or its child domain. If the query does not belong to it or its child, it returns an error indicating the requested host or service is not available. If the query belongs to it, it resolves the query. If the query belongs to its child domain, it provides a referral to the child domain's name server. It only provides referrals for its child domains. It knows nothing about its grandchild domains. If its child domain has child domains, the child domain will be responsible for providing referrals to its child domains. We need to create authoritative name server records in the domain zone file. For example, if we want to create name server records for the example domain, we need to add authoritative name server records in the example domain zone file. The name server record uses the following syntax. This field defines the maximum time resolver systems can cache this record. If we leave this field blank, DNS uses the default value of the TTL directive. This field defines the class type. This field defines the record type. The domain name field defines the domain for which it configures the authorized name server. If we leave this field empty, DNS uses the previous record's name field's value in this field. Usually, NS records are placed just after the start of authority record. Therefore, if we keep this field empty, DNS picks the start of authority record's name field's value as the default value for this field. In the start of authority record, administrators usually use a single @ sign in the name field. DNS replaces the @ sign with the value of the origin directive. With this setup, the start of authority record automatically receives the domain name from the origin directive, and NS records receive it from the start of authority record. In our example, we configured the domain name example.com in the origin directive. From this directive, DNS will automatically configure the domain name field of the start of authority record and NS records. The authorized name server field defines the authorized name server for the domain we configure in the domain name field. This record configures the name server ns1.example.com as the authoritative name server for the domain example.com. If the authoritative name server is available within the domain, we also need to create a host record for it. A host record maps a service or a host to an IP address. As I mentioned earlier, a resolver system can access a name server only from its parent domain. Because of this, we need to create an NS record for each name server in its parent domain zone file. An NS record that we create in the parent domain zone file is known as a referral name server record or a glue name server record. It sticks the child domain's name servers with the parent domain's name server. It uses the same syntax the authoritative name server record uses. The only difference between a referral or glue nameservers record and an authoritative nameservers record is that in the referral nameserver record, we use the domain name for which we are creating the referral in the domain name field. For example, if we want to create a referral name server record for the XYZ domain, we will use the XYZ domain's fully qualified domain name here. Since the referred domain is a child domain of this domain, we must have to create a host record for it also. If we create a glue record without the host record for the child domain's name server, the resolver systems cannot access the child domain's name server. Let us take an example to understand it. A resolver system wants to resolve the name ftp.xyz.example.com. By default, resolver systems only know the IP addresses of root nameservers. They save them statically in library files. For example, Linux saves root nameservers' IP addresses in the /var/name/name.ca file. The resolver system sends the query to the nearest root nameserver. The root nameserver provides a referral to the CNAME nameserver. The referral includes the CNAME nameserver's IP address. From the referral, the resolver system learns the CNAME nameserver's IP address and sends the same query to the CNAME nameserver. The CNAME nameserver provides a referral to the example nameserver. The referral includes the example nameserver's IP address. From the referral, the resolver system learns the example nameserver's IP address and sends the same query to the example nameserver. The example nameserver provides a referral to the XYZ nameserver. Since the query belongs to the XYZ nameserver, it resolves the query. Now, Let us suppose the administrator forgets to add the IP address in the glue record of xyz.example.com in the zone file of example.com. In this situation, the example nameserver will provide a referral to the XYZ nameserver without its IP address. Since the resolver system does not know the IP address of the XYZ nameserver, it has to resolve this name first. To resolve this name, it follows the same steps. Since the resolver system can get the XYZ nameserver's IP address only from the example nameserver and the example nameserver does not provide it, the resolver system will keep repeating this process. It creates an infinite loop of queries between the resolver system and the example nameserver. To avoid this situation, you should always add a host record for the referral nameserver in the parent domain nameserver's zone file. DNS is an essential service. You should configure at least 2 nameservers for each domain. You should configure the primary name server within the domain. You should configure the secondary name server outside the domain in a different geographical location. This setup allows resolver systems to access resources even if the primary name server fails. We use the same syntax to add an NS record for the backup name server. If the backup name server is available within the domain, we also need to add a host record for it. If the backup name server is available outside the domain, we do not need to add a host record for that. As mentioned earlier, in a DNS system, only authoritative name servers can resolve queries. Because of this, we also need to configure the backup name server as the authoritative name server for the domain. If we do not do this, a situation called lame delegation occurs. A lame delegation occurs when an NS record points to a name server that is not authorized to answer for the domain. In this example, we configured a backup name server, ns1.example.net. We need to configure this name server as the authoritative name server for the domain example.com. To authorize this name server for the example domain, we need to configure this name server as the slave name server for this domain. A name server can act as a primary name server for one domain and a backup name server for another domain at the same time. This flexibility allows administrators to use existing name servers to configure backup name servers for other name servers. Let's take an example. Suppose we have 2 primary name servers ns1.example.com and ns1.example.net for the domains example.com and example.net. We can configure the ns1.example.com name server as the backup name server for the ns1.example.net name server and the ns1.example.net name server as the backup name server for the ns1.example.com name server. This setup allows us to configure backup name servers without adding any additional name servers to the network. MX records define mail servers. It uses this syntax. The domain name field defines the domain for which this record will define the mail server. Similar to an NS record, if we leave this field empty, the record will inherit its value from the previous record's name field. The TTL field defines the maximum time resolver systems can cache this record. If we leave this field empty, the record uses the TTL directives value. In this example zone file, we have 2 MX records. In the first record, we define this field's value. In the second record, we left this field empty. Because of this, the first record will use the defined value. The second record will use the TTL directives value. The class field defines the class of the record. The resource type field defines the record type. The preference field defines the priority of mail servers. If you configure multiple mail servers, you can use this field to define the order in which they should be used. You can use any value between 0 and 96,535. In order, a lower value has higher priority than a higher value. Typically, administrators use values in multiples of 10. They use the value 10 for the most preferred mail server, 20 for the second most preferred mail server, and so on. This method allows them to add additional MX records without changing the existing order. In this example, we use this field to configure the mail server mail.example.com as the main mail server and the mail server mail.example.net as the backup mail server. To define mail.example.com as the main mail server, we use the value 10, which is the lowest in the configured priority order. We used value 20 for mail.example.net to define it as the backup mail server. The mail server field defines the email server for the domain we configure in the domain name field. In this example, we configured 2 mail servers mail.example.com and mail.example.net for the domain example.com. We configured mail.example.com as the primary mail server and mail.example.net as the backup mail server. Our primary mail server is available within the domain. Our backup mail server is available in the external domain. With this configuration, if the primary mail server fails, the backup mail server will receive mail for the domain and forward them to the primary mail server as soon as it will come online again. If the mail server is available within the domain, we also need to add a host record for it. For example, this mail server is available inside the domain. Therefore, we need to add a host record for it. If the mail server is available outside the domain, we do not need to add a host record for that in the zone file of this domain. We need to add a host record for it in the zone file of that domain. In our example, we do not need to add a host record for mail.example.net in the zone file of the example.com domain. We need to add a host record for mail.example.net in the zone file of the example.net domain. We need to create host records of all resources available within the domain in the domain's zone file. If a resource is available in the external, parent, and child domains, we don't need to add that resource's host record in the domain's zone file. There is only one exception to this rule. We need to add a host record for the child domain's nameserver record. In this domain tree, we have 3 domains in one branch and 2 domains in another branch. The example domain is the parent of the XYZ domain and child of the CNAME domain. We need to create host records for these resources in the zone file of this domain. We will create host records for these resources in the zone file of this domain. Same way, for these resources, we will create host records in the zone file of this domain. Since the XYZ domain is the child domain of the example domain, we need to create a host record for the XYZ domain's nameserver in the example domain's zone file. Similarly, we need to create host records for all nameservers in their parent domain's zone files. Besides nameserver records, we don't need to add host records of any domain in its parent domain's zone file. To add a host record, we use the following syntax. The name field defines the name of the host or service whose IP address we want to make publicly accessible. If we use a relative name here, DNS automatically converts it into a fully qualified domain name by adding the origin directives value to it. The TTL field defines how long other name servers and resolver systems can cache this record. The class field defines the class type of this record. The resource record type field defines the type of record. The A record maps an IP4 address with the name of a host or a service. The quad A record maps an IP6 address with the name of a host or a service. The IP address field defines the IP address we want to map with the name defined in the name field. We can map multiple IP addresses with the same name. This feature is used when we run the same service on multiple hosts. If the same service is available on multiple hosts, we need to map their IP addresses with the service name. For example, if we configure the same web service on 3 hosts for backup and redundancy purposes, we need to map all 3 hosts' IP addresses with the service name. If we map multiple IP addresses with the same name, DNS provides an IP address for the name in a round-robin or random order. You can define this order by configuration directives. We can also map multiple names with a single IP address. You can use this feature when you run more than one service on the same host. For example, if you have a small website and use only a few email addresses for management and communication purposes, you can run the mail, web, and FTP services on the same server. This setup allows you to save the cost of additional servers. Let us understand this feature through our example. Suppose we configure the mail, web, and FTP services on a single server whose IP address is 192.168.0.2. In this situation, we need to map these services with the IP address 192.168.0.2. The CNAME resource record type assigns an alias name to the name of an existing host or a service. The alias name field defines the name you want to use for the existing name defined in the canonical name field. The canonical name field defines the actual name which you want to access by an alias name defined in the alias name field. This record type is used when you want to access a service from another name or hide your internal network structure from external users. Let's understand it through our example. Suppose we run the web service on a host called MyWebServer. In this situation, we can map the name www with the name MyWebServer. After this, DNS will translate the name www into the IP address of MyWebServer. Users will access the web service running on the IP address of MyWebServer by using the name www. Usually, administrators configure a web server to serve websites with and without the www. This setup needs a CNAME record in the zone file for the web service. To achieve this goal, you need to add a host record for the domain name, and then you need to configure the www as the alias name for the domain name. A zone file only translates names into IP addresses. It does not run or provide any other service. If you add an alias name for a service, you also need to configure that service to respond to both canonical and alias names. In this example, you also need to configure the web server to respond on both names www.example.com and example.com. Since we configured this system as the primary nameserver for the example domain, we need to create a forward lookup zone file on this system. Create a forward lookup zone file and open it for editing. Use the same name for the file you used in the zone configuration directive. Although comments are optional, you should use them. They explain the meanings of directives and configuration settings. Create the time to live configuration directive. Set its default value to 2 days. DNS will automatically use this value in all empty TTL fields. Create the origin directive. Configure the domain name as its value. DNS will use it to convert relative names into fully qualified domain names. Create a start of authority record. This record is compulsory. We can create only one start of authority record in a zone file. This record defines the domain's properties and authority nameserver for the domain. Use parenthesis to define zone transfer specific options in multiple lines. Add a comment with each option to explain its meaning. Create nameserver records. First, create a nameserver record for the primary nameserver. If the domain has a backup nameserver, add a nameserver record for the backup nameserver. After nameserver records, create mail exchanger records. Add an MX record for the primary mail server. If the domain has a backup mail server, add an MX record for the backup mail server. Finally, add host records for all services and hosts that are available inside the domain. If the backup name server and mail server are available inside the domain, add host records for them. If they are available outside the domain, do not add host records for them in this zone file. Add some host records for testing. These hosts do not need to exist on the network. You can create any resource records for testing. Save the file. We can use the cat command to view and verify the zone file's contents. The default firewall configuration does not allow this system to accept DNS queries from other systems. The default firewall configuration will block all incoming DNS traffic. Add a rule in the firewall to allow incoming DNS traffic. DNS will not read the new zone files until we restart the named service. Restart the named service. To verify the configuration, we can use the host command. This command uses the configured nameserver to translate the specified host name. The output of this command verifies the locally configured nameserver is translating names correctly. We can also use the dig command. This command sends name resolution queries to the configured DNS server and displays the response. As we can see here, it received this response from the nameserver configured on this system. Now, let's verify this configuration from the DNS client system. To verify this system is configured as a DNS client, we can check the resolve.conf file. Use the dig command to send a DNS query to the configured nameserver. As we can see here, the nameserver is resolving DNS queries correctly. We can also use the host command to verify the nameserver. Send some DNS queries. As we can see in the output, the nameserver is translating queries correctly. It verifies the nameserver configuration. Now let's switch back to the server. Send a DNS query to translate a name into the IP address. Now send another query to translate an IP address into the name. As we can see here, the nameserver translates the name into the IP address, but it fails to translate the IP address into the name. This happens because so far, we configured only forward mapping that translates names into the IP address. If we want this nameserver to translate IP addresses into names, we need to configure reverse mapping. Before we configure reverse mapping, let's understand what the mapping is and how it works in the DNS system. In the DNS system, there are two types of mapping: Forward mapping and reverse mapping. The DNS system was mainly designed for forward mapping. In forward mapping, name servers translate names into IP addresses. Later, they added reverse mapping to the DNS system for security and diagnostic purposes. In reverse mapping, name servers translate IP addresses into names. It is an optional feature. Although it is an optional feature, you should use it. In modern computer networks, many services use it to authenticate the source address. For example, email service uses it to verify the source email address. If you do not configure reverse mapping for a domain, other domains will not accept emails originating from it. In forward mapping, when an end device wants to know the IP address of a remote device or service, it sends a name resolution query to the resolver system. The resolver system forwards that query to all name servers in a sequence until it finds the answer. This sequence is known as the DNS namespace. In other words, a DNS namespace is a sequence of domain names arranged in a hierarchy. A domain name is a text label for the domain. In this hierarchy, the root domain stands at the top. It uses a null character as the label. You can write a resource name with or without its parent's domain name. If you write its name with parent domain names, it is called a fully qualified domain name. A fully qualified domain name uses dots to separate domain names. It starts with the resource's name and ends with the root domain's name. Since the root domain uses a null character as the name, it always ends with a dot. This is an example of a fully qualified domain name. In this name, FTP is the resource name. It is the child of the example domain. The example domain is the child of the CNAME domain. The CNAME domain is the child of the root domain. Each domain uses an authoritative name server to resolve queries for resources available inside it. If it has a child domain, it does not resolve queries for the child domain. It provides a referral to the child domain's authoritative name server. Only authoritative name servers can resolve queries. If a name server is not authoritative for a domain, it provides a referral to the next authoritative name server in the sequence. Since all authoritative name servers work in a hierarchy, a resolver system can easily reach the authoritative name server that can resolve its queries. This process is an example of forward mapping. In reverse mapping, a resolver system resolves an IP address with the name. Suppose the resolver system wants to know the name of the IP address 192.168.0.3. For this, it follows the same steps it uses in forward mapping. It sends the first query to the root name server and follows the referral until it gets the answer. Unlike fully qualified domain names, IP addresses do not include domain names. An IP address includes two types of addresses, the network address and the host address. For example, in the IP address 192.168.0.3, the network address is 192.168.0, and the host address is 3. Network addresses are used to organize and find IP addresses. Host addresses are used to provide a unique identity to an endpoint or a resource. A network address is like a domain name. A host address is similar to a resource name. Since IP addresses do not include domain names, developers used a different approach to build a domain tree for IP addresses in the DNS namespace. They created a domain called ARPA as a child domain of the root domain and used it to build a domain tree for IP addresses. There are two versions of IP addresses, IP4 and IP6. To keep the IP addresses of both versions separate, they created two additional domains as the child domains of the ARPA domain. For IP4 addresses, they created the in-address domain. For IP6 addresses, they created the IP6 domain. They constructed the domain tree for both versions inside their respective domains. To construct a domain tree for IP addresses, they used network addresses. But there was a problem. Unlike domain names which are written from right to left in fully qualified domain names, network addresses are written from left to right in IP addresses. To solve this problem, they flipped the IP addresses in the domain tree. For example, the IP address 192.168.0.3 will be written as 3.0.168.192 in the domain tree. The DNS system uses fully qualified domain names. A fully qualified domain name includes all parent domain names. To convert this address into the fully qualified domain address, we need to write its parent domain's name with it. 192.168.0.3 is an IP4 address. The parent domain of IP4 addresses is in address. The in-address domain is the child of the ARPA domain. The ARPA is the child domain of the root domain. Because of this, the fully qualified domain name of the IP address 192.168.0.3 will be 3.0.168.192.in address ARPA. If the resolver system wants to know the name of the service or host using the IP address 192.168.0.3, it sends the first query to the root name server. The root name server provides a referral to the ARPA name server. The ARPA name server provides a referral to the in address name server. The in address name server provides a referral to the 0.168.192 name server. The 0.168.192 name server provides the name associated with host address 3. This process is an example of reverse mapping. Authoritative name servers use zone files for translation. There are two types of zone files: forward lookup zone file and reverse lookup zone file. A forward lookup zone file maps names with IP addresses. A reverse lookup zone file maps IP addresses with names. Forward lookup zone files are compulsory. You need to create a forward lookup zone file for every domain. In that file, you need to add records for all resources whose names you want to translate. Reverse lookup zone files are optional. You only need to create a reverse lookup zone file for the domain which runs services that need reverse mapping. In that file, you need to add records only for those services that need reverse mapping. If you do not want to provide reverse lookup for a domain, you do not need to create a reverse lookup zone file for it. There are two versions of IP addresses, IP4 and IP6. You can use a single forward lookup zone file to map names with IP addresses of both versions. But you cannot use a single reverse lookup zone file to map both versions' IP addresses with names. You need to use separate reverse lookup zone files for both versions. You only need to create a reverse lookup zone file for the IP version your domain uses. For example, if your domain does not use IP6 addresses, you do not need to create a reverse lookup zone file for IP6 addresses. A reverse lookup zone file uses the same configuration style as a forward lookup zone file. You can easily create a reverse lookup zone file from the forward lookup zone file. As mentioned earlier, a forward lookup zone file is compulsory for each domain. You need to create and configure it before you create and configure the reverse lookup zone file. If you have a forward lookup zone file, you can easily create a reverse lookup zone file from it. Let us understand this process through an example. Linux saves zone files in the /var/name directory. This is the forward lookup zone file of the example.com domain. Create a copy of this file. You can choose any name for the copied file. Usually, administrators prefer the domain's network ID with a DB extension. It makes finding and managing zone files easier. In our example, the network ID of the example domain is 192.168.0. Flip this address and add a DB extension to it. Open this file. This is a line comment. The name server will ignore it. Change it to indicate that this is a reverse lookup zone file. The next is the TTL directive. It defines the maximum time other name servers or resolver systems can cache records served from this file. Keep it as it is. The next is the origin directive. It defines the fully qualified domain name. As explained earlier, in reverse mapping, a fully qualified domain name is the complete network address of the domain. Specify the complete network address of the domain. Zone files are not case sensitive. You can specify a name in both upper and lower cases. The next is a start of authority record. It defines the characteristics and properties of the domain. The next are the NS records. These define authoritative name servers for this domain. The start of authority and NS are compulsory records. These records are the same in both the forward and reverse zone files. You do not need to make any changes to these records. Keep them as they are. Next are mail server records. We do not need them in the reverse lookup zone file. Remove these records. Next are the host records. In a reverse lookup zone file, we use the PTR record type for these records. Unlike forward mapping, reverse mapping is not compulsory. We do not need to add PTR records for all hosts. We need to add PTR records only for publicly accessible services such as mail, web, and FTP. Remove all host records whose names you do not want to make publicly visible. In the remaining records, change the resource record type to PTR. Now, we need to interchange the resource name and IP address fields values. While doing this, we need to take care of the zone file's automatic name conversion rule. Remember, in a zone file, if a name does not end with a dot, the zone file automatically converts it into a fully qualified domain name using the origin directives value. We use this rule in the resource name field. In it, we specify only the host name and let the zone file convert it into a fully qualified domain name using the origin directives value. Pick only the host addresses from IP addresses and place them in the resource name field. Because of the same rule, we need to convert these resource names into fully qualified domain names. If we do not do this, the zone file will automatically convert them into fully qualified domain names using the origin directives value. For example, it will convert this name into this name. It will be an incorrect configuration. Convert all resource names into their fully qualified domain names. That's all we need to do in this file. Save the file. Now, this file is ready to translate IP addresses into names. To configure reverse mapping, we need to add a reverse zone configuration in the named conf file. Open this file. Go to the zone section. Create a new zone after the forward zone configuration. A reverse zone uses the same configuration a forward zone uses. Configure type option to master. Specify the zone file name. You need to create this file in the /var/name directory. Configure the value none in the allow transfer option. We will configure this option later. Save the file. Now we need to create the zone file for the reverse mapping. To create it, we can use the forward zone file as the template. Create a template from the forward zone file. For the reverse zone file, use the same name you configured in the reverse zone configuration. Open the file. You can update comments or can leave them as they are. Leave the time to leave directive as it. Update the origin directive. DNS will use this name to convert all relative names into fully qualified domain names. We do not need to update or change the start of the authority, nameserver, and mail exchanger records. Leave them as they are. Update the resource record type of host records. Now exchange the resource names and IP addresses. Use only the host portion of IP addresses. Do not add a dot at the end of the host addresses. DNS will automatically convert them into fully qualified domain names by adding the origin directives value. We need to convert these names into fully qualified domain names manually. Add domain name with all names. Save the file. DNS will not read this file until we restart the name service. Restart the name service. Now send some DNS queries to translate IP addresses into names. As we can see here, now the DNS server is translating IP addresses into names. It verifies that the reverse mapping has been configured correctly. Now test it from the DNS client system. Perform the same tests from the client system. As we can see here, the nameserver is translating names into IP addresses and IP addresses into names. It verifies the nameserver is correctly configured to provide forward and reverse mapping. A slave or secondary nameserver fetches zone files from the primary or master nameserver. To configure a secondary or slave nameserver, first, we need to configure the primary or master nameserver to transfer zone files to the secondary or slave nameserver. On the master nameserver, open the name.conf file. Go to the zone section. Configure the allow transfer option in both zones. Remove the value none and add the secondary or slave nameserver's IP address in this option. Save the file. Restart the name service. Now go to the system you want to use as a secondary or slave nameserver. Open the /etc/name.conf file. Configure the listen on port 53 and the allow query options. Go to the zone section. Here we need to add two zone configurations, one for the forward mapping and another for the reverse mapping. In both zones, configure the type options value to slave. DNS saves the files it receives from the master nameserver in the slave directory. The third option is masters. DNS automatically sends zone transfer requests to the nameservers specified in this option. Configure the primary nameserver's IP address in this option. By following the same steps, you can configure the reverse lookup zone. The reverse mapping is optional. Because of this, you need to configure a reverse zone here only if you configured the reverse mapping on the primary nameserver. Save the file. Go to the /var/name/slaves directory and list the content. As we can see here, at this time, this directory has no zone configuration files. The nameserver will not read the new zone configuration until we restart the name service. Restart the name service. Now list the content again. The nameserver automatically fetched these zone files from the master nameserver. This nameserver will use these zone files to resolve DNS queries when the primary nameserver fails. It will work as a backup nameserver for the primary nameserver. DNS clients know nothing about this nameserver. We need to update their IP configuration to use this nameserver as a backup nameserver. Open the IP configuration on the client system. Add the backup nameserver's IP address. Restart the connection. Verify the updated IP configuration. Now send a DNS query and check the nameserver's IP address in the output. As we can see here, this query has been resolved by the primary nameserver. Now go to the primary nameserver and stop the name service. Now send another DNS query and check the nameserver's IP address in the output. As we can see here, this time, the query has been resolved by the backup nameserver. It verifies the secondary or backup nameserver configuration. The backup nameserver will resolve queries only until the primary nameserver remains down. As soon as the primary nameserver comes online again, the client system will stop using the secondary nameserver. To verify it, start the name service on the primary nameserver. Now test from the client system again. As we can see here, this time, the query has been resolved by the primary nameserver. It verifies the secondary nameserver translates DNS queries when the primary nameserver is down. That's all for this video. If you have any suggestions, comments, or feedback about this video, please share them with us in the comment section given below.